Hello, it's Stat 134, Lecture 25. The last two times we did section 3.4, actually 4.4, on the change of variable rule. And so remember, if we have g a many-to-one function that's transforming a random variable x, we see that for y to be in dy, x is in dx at different values of x, and so that is mutually exclusive. So we have the addition rule, and we can write the probability that y is in dy as a sum of three terms, and dividing through by dy, and noting that probabilities can't be negative. So we have the absolute value of the derivative on in the denominator. We get the change of variable rule. And the only thing this is missing is that we evaluate x at g inverse of y. So because the density for y is a function of y, not x. Secondly, last time we did moment generating functions. This is not in the book, and it's defined as the expectation of e to the tx. The theorem we covered last time is that if an MGF exists in an interval around 0, then the kth derivative evaluated at t is 0 is the kth moment. So for example, if x is Poisson, you can find the moment generating function of x using the definition, taking an infinite sum for your expectation, and pulling out e to the minus mu, and writing it so that we have a Taylor series, e to the mu e to the power t, and then just a little algebra shows you that the moment generating function is e to the mu parenthesis e to the t minus 1, and this is for all t. So if we take the derivative of this and evaluate it at 0, we see that we get mu, which is what we're supposed to get. So today we're going to look at some key properties of MGF. We're going to review the concept test from 2 times ago, and the CDF of a mixed distribution. So the key properties of the MGF, firstly, if an MGF exists in an interval containing 0, the kth derivative evaluated at t is 0 is the kth moment. That's what we did last time. Another very important property that you'll show in the homework is that if x and y are independent random variables, then the MGF of x plus y is the product of the MGFs. And another one is about the uniqueness of the MGF. And it says that if you have two MGFs that are equal for t in an interval around 0, then the CDFs are the same. In other words, x and y have the same distribution. So to prove this, you need to know how to invert an MGF to get a CDF, and that involves a Fourier transform, so we won't get into that, but you can see why the MGF has information about the CDF just from looking at a discrete example. So for the MGF, the e to the xt terms tell us the value of x. So we know all the values of x, and the coefficient in front of the e to the xt gives you the probability that x is that value. So the MGF has all the information about the distribution. So property A here is useful for finding the expectation and the variance. That's mainly how we'll use it. Properties B and C allow us to prove, for example, that the sum of independent Poisson is Poisson or even you can prove the central limit theorem with that. So let's take a look at an example. So if x1 is Poisson mu1 and x2 is Poisson mu2 independent, show that x1 plus x2 is Poisson mu1 plus mu2. So we've already worked out what the MGF is for x1 and x2. So just using property B above, the MGF for the x1 plus x2 is the product of the MGFs, and that has the M. So that from that you can see that this is the MGF of Poisson mu1 plus mu2. It has that form. So by the uniqueness, that shows that x1 plus x2 is Poisson mu1 plus mu2. So again, if you can show that the MGF of x1 plus x2 is the MGF of a Poisson, then x1 plus x2 must be a Poisson. So if x is a random variable and a is a constant, I asked you to show that the moment generating function of ax of t is mx of at, and so this is just using the definition and doing a little algebra here. It's very easy. More interestingly, if x is gamma, so we know the MGF of gamma, let x be exponential lambda and a positive constant, show that y equals ax is also exponential, and specify the new parameter. So here we use the fact we just showed that the moment generating function of ax of t is the moment generating function of x of at, and so since x is exponential, which is gamma with r is 1, this is lambda over lambda minus at, and this is for at less than lambda, and dividing top and bottom by a, so that it's going to be in the form of the moment generating function for gamma, we see that this is the MGF for exponential lambda over a. So by the uniqueness of MGF, this shows that ax is exponential lambda over a. So next, that finishes moment generating functions. Now we go over the concept test responses from last time. So we have v standard normal. What's the distribution of v squared? So the way that one student did it was by using the change of variable rule, ignoring the constant and recognizing the variable part of a gamma. So that's great. Another student said, okay, v takes values between minus infinity and infinity. If I square that, that takes values between 0 and infinity. And so it can't be B or C. So it's either A or D, and they guessed A correctly. Other students said other interesting things. It's like a gamma distribution and a Gaussian distribution mixed, very creative. If we have a normal distribution and square our random variable, then we'll see that it stays normal. I guess we'll see that one day. So now let's hop over to section 4.5 now. So the cumulative distribution function. So x is a random variable. Remember that the CDF is a probability that x is less than or equal to x, and its use is to describe a distribution. So for example, for uniform, the CDF is linear between A and B. So I asked you guys to find the CDF of Bernoullian exponential. And so the CDF of a discrete is always going to be like a stairs. And for exponential, notice that the probability that t is less than or equal to t, which is the CDF, is 1 minus the probability that t is greater than t. The probability that t is greater than t is the survival function e to the minus lambda t. So I just graphed 1 minus e to the minus lambda t. Then we consider mixed distributions, which are part continuous, part discrete. So for example, say t is exponential lambda and c is a positive number. Let x be t if x is less than c, and c if x is c. So x takes values less than c and including c. Or you could think of it as the min of t and c. So it doesn't take anything larger than c, or t is killed by c. So you can imagine the exponential, whose density I've kind of written here, but past c, instead of having the green dotted line, all the mass is concentrated at c. So all the mass is the probability that t is greater than c, which is e to the minus lambda c. And from this, you can make the CDF. So finally, to test your understanding, we have a concept test here. Suppose you're trying to discretely leave a party. Your time to leave is uniform from 0 to 2 minutes. However, if your walk to the exit takes more than 1 minute, you run into a friend at the door and must spend the full 2 minutes to leave. Let t represent the time it takes you to leave. True or false, the graph of the CDF is as shown. Well, I would just go ahead and try and graph the density and then the CDF. So the only values that t can take are non-zero values that t can take are between 0 and 1 and 2. And so there are no values like if you arrive at 1.5 minutes, then you're definitely waiting 2 minutes. So the CDF looks like what I've drawn below, and then the CDF would also be what I've drawn below. So it's linear from 0 to 1, and then between 1 and 2 it stays the same, and then there's a jump at t is 2. So that's the show for today. Have a great spring break, and I'll see you on the other side.